Continuation of the previous lecture number 8. If you cannot listen the lecture number 8, in that case, I always recommend you to listen the lecture number 8, then you start to listen the lecture number 9, because the shortage of time you cannot complete the theorem of division algorithm, and this particular lecture will continue the proof of the division algorithm. Okay, so in the last lecture we have completed the portion. The result R should be lesser equals to 0 to B. Here we can start. Is the very important result is that existence of uniqueness of the integer q and r. Again we repeat the division algorithm. Given integer a and b with b greater than 0, a not equals to 0, there exists unique integer q and r such that a equals to bq plus r 0 lesser equals to r lesser equals to b. In the previous lecture we proved the result r, which is known as the remainder should lies between 0 to b. B is the dividend. Okay, so we move to the next part of the theorem, establishment of uniqueness of q and r. That means when we use the division algorithm, when we divide a by b, the quotient and the remainder should not be different for the for a particular case. That should be unique, that should not be different. You should remember this. Exactly for that reason here we use the theorem, proof of the theorem. When you can learn the proof of the theorem, in that case you are clear about that. When you divide some quantity by another, when you divide by an integer with the another integer, in that case the quotient and remainder should be the same. The quotient and remainder should be unique. Here we prove the uniqueness of the theorem. So we start to prove the uniqueness of the theorem. Let us consider or suppose that a has the two representation. Here we just consider, you can write a in two different form. One is qb plus r, another one is q dash b plus r dash. According to the previous lecture we have already proved that the remainder r should be lies between 0 to b, and another remainder, if we consider there exists another remainder r dash, that should be also lies between 0 to b. Okay, so we start the continuation of the proof. Next we move to the next step. Just we subtract these two quantity, the result should be a should cancel out, the result should be q minus of q dash b and plus r minus r dash equals to 0. If we transpose r minus r dash from right to left, in that case the result should be r minus of r dash. Here we mention this result. Next, just we make a module, absolute value of this quantity. When we consider the product of two quantity, the result, when we take the modulus value of this quantity, that should be separate, and q minus of q dash. So here we use the modulus sign and here we use the modulus sign. That means we are just interested to take the absolute value, not the sign. That means the only the positive value. The question arises in your mind is that why we should not consider b's module absolute value, because we have already considered that b is a non-negative integer. So if we consider here the modulus value, in that case whatever may be the modulus value, that should be the value of b. So from this portion we can move to here. According to the result, we have already learned that the r dash is lies between 0 to b, and and r should lies between 0 to b. If we multiply it by minus, in that case the change of the inequality becomes minus b less than minus r lesser equals to 0. If we add these two quantity, what happened? R dash minus of r should be lies between minus b to b. Okay, I think it's clear, because minus r is lies between minus b to 0 and r dash is lies between 0 to b. That means if we add these two quantity, the result should be lies between minus b to b. R dash minus of r dash minus of r result should lies between minus b to b. So if we consider the modulus value of r dash minus r of r, that means we just consider the absolute value, we are not interested to take the negative value. In that case, r dash minus of r should be lesser b. Okay, so that's very important is that since q dash minus of q should be lesser 1, the question is that why we consider q dash minus of q is lesser 1, because if r dash minus of r is less than b, if r dash minus of r is less than b, this portion, okay, r dash minus r is less than b, that means if we put this value here, the result is less than b, the result is less than b, that means you have to multiply the quantity b with another quantity that should be a proper fraction, otherwise the result should be greater than b, because if this portion is an integer, if this portion is an integer, in that case the result should be greater than b. But according to our assumption, the r dash minus of r, according to our calculation, the result of r dash minus of r, which is less than b. So these are q minus of q dash should be, these q minus of q dash should be less or equals to 1. Exactly for that reason, here we use q dash minus of q is less than 1. Okay, so if we consider q dash minus of q is less than 1, and we have already learned that q and q dash are the integer, that means the difference of two integer, if the difference of two integer absolute value is less than 1, it's represent that this value should not be other than 0. Exactly for that reason we consider q minus of q dash that should be equals to 0. If q dash minus of q is equals to 0, it's represent that q and q dash are q should be equals to q dash. If q equals to q dash, that's very important, q equals to q dash, that means if we put this value of q minus of q dash here, in that case the left hand side of a mod of r minus r dash should be 0. If the left hand side is equals to 0 and r dash both are the integer, in that case the result should be equals to r equals to r dash. That means when we start our problem, we just recognize that q and q dash and r dash are the different integer, but when we deduce this proof of this statement, we have clearly found that this result should not be distinguished, this result should be equals to. Exactly for that reason we always use the result should be unique, q and q dash should be unique. So it's the another theorem, it's the you can also say that it's also some books use this theorem as an as a division algorithm theorem. In the last theorem we proved by b is greater than 0, that means you always consider that the dividend is always should be positive, that should not be happen for every case. Exactly for that reason here we construct the upgrade form of the division algorithm, that is the original division algorithm, where b not equals to 0. That means when you divide some quantity by another quantity, this another quantity or the dividend should be not equals to 0. Exactly for that reason, we can find a equals to bq plus r, where the value of r should be, that means it is called the remainder. Remainder should be lies between 0 to mod b. 0 to mod b. We start our proof exactly in the previous concept, so we can easily move to the step every step very fast. With the previous theorem already established, it is enough to consider the case in which b is a negative. Then in the previous class we just proved for the positive case, that means if we consider in the negative case in this theorem, then this result should be applicable for not equals to 0. And that means then mod b is greater than 0. By the previous theorem there exists a unique integer q dash and r. Okay, So you can write A equals to mod B plus Q dash plus R according to the previous theorem. So if B is itself is a negative number, so you can write this one is minus B Q dash plus of R. So A equals to BQ plus of R. If we consider Q equals to minus Q dash, this minus Q dash is represented by Q, then we can write A equals to BQ plus of R, nothing to do. That means when we prove this result, first we prove the previous theorem, next we prove for the case when B itself is a negative. In that case, when B is itself is a negative, this model should be minus B. Exactly for that reason, here we consider this cases. Okay, exactly for that reason here we consider these cases. So for your understanding, here we give some example to clear your idea related to the division algorithm. Q and R, you have to find Q and R, where A is minus 22 and 10 and B is 3. That means when we divide A by B, that means it may be minus 20, it may be 2, it may be 10, and divide by 3, what should be Q and what should be R. This minus 20 equals to uniquely represent as 3 into minus 7 plus of 1. আমরা অবশ্যই মনে রাখবো যখন আমার ডিভাইজার নেগেটিভ থাকে তখন আমরা এক ঘর বেশি কনসিডার করি। দ্যাট মিনস নর্মালি এটা যদি 20 হতো তাহলে আমরা কি করতাম 2 into 7 14 প্লাস 6 হতো রিমাইন্ডার। কিন্তু যেহেতু এখানে নেগেটিভ আছে, তাই আমি যখন কোশিয়েন্ট বার করবো যত বার ডিভাইড করা উচিত তার থেকে একবার বেশি ডিভাইড করে নেবো। সো দ্য রেজাল্ট বিকামস 3 into minus 7 plus 1 minus 20, 1 plus 1, that should be minus 20. So Q is minus 7, R is 1. This representation is unique. Q যদি মনে করে এখানে আমি লিখবো 3 into say 2 into minus 7 minus 14 minus 6, that should not be considered because R should be a non-negative integer. Okay, so this representation is unique. Similarly, if we divide here, we miss the term 20, 2 divided by 3, 2 divided by 3, so 2 should be written as 3 into 0 plus of 2, remainder should be 2, so R is 2 and Q is 0. When we divide 10 by 3, the result is 3 into 3 plus of 1, Q is 3 and R is 1. Another example for you, find Q and R. Exactly for this, here we consider the negative cases for your understanding, minus 20 and minus 3. In that case again we repeat the concept, minus 3 into minus 7 plus 1, and that is not the case. So here we consider when we divide by 3, the result should be 7. Here is a mistake in the result, so here we consider when we divide by 7, that should be 6, so the remainder becomes 7. Okay, so here the result should be 6 and the remainder should be 3. Okay, next one, when we divide 2, that is minus 3 into 0 plus 2. When we divide by 3, that should be minus 3 into minus 3 plus 1. So Q is minus 3 and R is 1. There is a mistake, so I have to modify this result. Okay, so that is the division algorithm. In the next class we will consider another theorem and related problem with the number theory. Thanks for listening.